Okay, enthalpy cycles. Enthalpy cycles. Right. So, if I asked you through experiment to determine the enthalpy change of combustion of methanol, then that would be quite straightforward. Okay, you use MC delta T, you measure the temperature change, then you divide by 1,000, then you divide by moles, and don't forget that when you're working out this enthalpy change of combustion, that it is going to be a negative value and that the units are kilojoules per mole, mole to the -1. Okay, so to determine that enthalpy change through experiment is quite straightforward, and that's on the previous video. Okay, but what if I asked you to determine the enthalpy change of formation of methanol? So this is the enthalpy change of formation of methanol instead. How would you do that? So let's first write a chemical equation for this. So if we're going to form methanol, we're going to make 1 mole, the formation of 1 mole of the compound from its elements in their standard states, carbon solid and hydrogen gas and oxygen gas. Remember, they go around in twos, the diatomic molecules. So this is for the formation of methanol. You never put a number here because you are forming 1 mole of a compound from its elements in their standard states. We need to balance it, so we've got 4 hydrogens, so we put a 2 there. We've got 1 oxygen, so we need half here because that will give us 1 oxygen. Right, okay, so that's the formation of methanol. And we want to determine the enthalpy change for this formation. Now, it is not possible through experiment to determine this enthalpy change. So you cannot determine enthalpy change of formation directly through an experiment like you can with combustion. And the reason why is because if we put carbon and hydrogen and oxygen together in a container, what's the chances of it actually making methanol? If we put carbon and hydrogen and oxygen together in a container, it's probably going to make carbon dioxide, water, methane. It's not going to make methanol. It's not going to be so specific as to make methanol. So the reason why you cannot determine the enthalpy change of formation directly through an experiment is because other products can be formed. There can be multiple products, for example, carbon dioxide, water, in this case, carbon dioxide, water, methane, in this case. Okay, so what we have to do is we have to find, if we're asked to determine the enthalpy change of formation of a compound, we have to do it indirectly rather than directly. We need to do it indirectly instead. And that means by using other enthalpy changes. And in order to do this, the method we use is called enthalpy cycles. Okay, and in order to do this, we need a definition. Okay, and the definition is we need to use Hess's Law. Okay, Hess's Law. So I'm going to just write down a definition here, okay? It's called Hess. His name is Hess, and it's his law. The law belongs to him. So we put Hess apostrophe law. Okay, and this definition is that the enthalpy change for a reaction, so this is just a definition that you need to learn. Enthalpy change for a reaction. The enthalpy change for a reaction is independent of the route taken. Is independent of the route taken. Provided provided the initial and final conditions are the same. Okay, Hess's law is independent of, it means that enthalpy change for a reaction is independent of the route taken, provided the initial and final conditions are the same. Remember, the reason why we're doing this is that if we cannot determine an enthalpy change through experiment, we need to find it indirectly, and we need to use enthalpy cycles in order to do that. Okay, so an example, if I give you an example, so if you were you're sat at home, okay, you sat at home, and your job is that you need to get to school or college. You need to get to college, okay, and you need to determine the enthalpy change for this reaction, the reaction of you going from home to college. Okay, so this Hess's law applies the first law of thermodynamics, that energy can be neither created nor destroyed, but it's transferred from one form to another. So it's not created or destroyed, but transferred. So you go from home to college. You may not go directly home to college. You may go from home to the shop to buy something, and then go to college, like that. Okay, and if we take this as your starting point, and this is your final point, your end point, you're going from here to here. Look, applying Hess's law, enthalpy change is independent of the route taken. Doesn't matter which route you take, as long as the initial and final is the same. If we start here and go here, this enthalpy change is exactly the same as going down and up, as going down and up. So if we were to call this enthalpy change 1, for example, and call this one enthalpy change 2, then going straight across, direct, going delta H for that reaction is exactly the same as going down delta H1 and up delta H2, because it doesn't matter which route you take. And this is called enthalpy cycles. Okay, so I'm going to show you an example. The best way to do this is through examples. Okay, so I'm going to show you an example of enthalpy cycles. So I've got an example here, already written out on a piece of paper. Okay, so let's see if you can see, if you can read this example. Right, so it says, calculate the standard enthalpy change of reaction given the following values, right? And the first thing you need to note, right, is first that this is the reaction we're trying to find. So this is like you at home, and this is like you at college. And this is what we're going to try and find. But we need to cycle to help us do that. The information that we have been given, can you see what that letter there says? The information we've been given is we've been given formation data. We've been given formation data, okay? So, the formation of calcium oxide. So we're going to form calcium oxide. We're going to make calcium oxide from its elements in their standard states. Calcium solid and oxygen gas. But we only need one O, so we just go half because we only need one O, okay? And that's the formation of calcium oxide. And that has the value minus 635.1 kilojoules per mole. And that's the formation of calcium oxide, okay? We've also got the formation of water. So we've got the formation making water. And we're going to make water from its elements, hydrogen gas and oxygen gas. But we only need one oxygen, so it's going to put half, like that. We're going to form water from its elements, and we're going to write the number by the side of the arrow. okay? And then finally, we've got the information we've got is the formation of calcium hydroxide. Okay, so watch really carefully now. We're going to form calcium hydroxide, 1 mole of calcium hydroxide. But all the elements are already written there. We've got calcium, solid, we've got hydrogen gas, and we've got oxygen gas as well. So all the elements are written. We don't need to write anything else. And we go minus 986.1 is the value. And that is the enthalpy cycle. Okay, we have now drawn an enthalpy cycle. And now we have to, an enthalpy cycle, right? We now have to apply, use Hess's law to determine the answer, okay? Now this is quite good if you've actually got a different coloured pen, like a highlighter, for example. It's quite a good idea to highlight this, okay? So we're going to go, this is what we want to find. That's what we want to find. Enthalpy change of reaction. And what we're going to do is we're going to start here. This is the start. This is the end, the final, start and end. We're going to go down these arrows, and we're going to go up this arrow. We're going to go down and up. We start here. That is the same as going down and up. Okay? So the calculation is going to be the enthalpy change of reaction. The enthalpy change of reaction, the standard enthalpy change. Okay, we're going to go down these two arrows. But the problem is these black arrows, these single black arrows, are going in the wrong direction because we want to go down and up. So if they're going in the wrong direction, we need to turn them around. And when we turn them around, what's going to happen to the sign of the enthalpy change? So this is minus 635.1. But I want to turn it around. I'm not going to do it on the enthalpy cycle though. I'm going to leave the enthalpy cycle. I'm going to turn it around down here, and I'm going to go 635.1 instead. Instead of minus, I'm going to put 635.1. I'm going to turn this one around, not on the enthalpy cycle. I'm going to do it down here, and it's going to become a plus 285.8. Okay, and then finally we go down. And now we need to go up. The single arrow, is it going in exactly the right direction? That's absolutely fine. We just keep the value minus 986.1. And you add all that up together, and then you'll get your answer for the enthalpy change for this reaction. And when you do that, the value should come out at minus, have a go at it on your calculator. It comes out as minus 65.2 kilojoules per mole. Minus 65.2 kilojoules per mole. Okay, let's try another example. So very, very similar. Okay, I can do this one a bit faster, but if you want to pause the video and have a go at yourself, that's a really good idea. Okay, we'll try and do it a little bit faster this one because it's quite similar. So we have got calculate the standard enthalpy change for this reaction. Okay, standard enthalpy change for this reaction. The data, the information we've been given is formation values. Okay, so we're going to form sodium NaNO3, and we're going to form it from its elements in their standard states, sodium and nitrogen gas and oxygen gas. And then we just need to balance it. We've got 2 Na, so just put a 2 there. We've got 2 N, that's good. And then the oxygens, we need in total 3 oxygens. Put the value by the side, minus 468 with the arrow. But this is for the formation of 1 NaNO3. We've got 2 NaNO3s, so we need to times it by 2 because we're forming 2 NaNO3s. Okay, and then we've got the formation of NaNO2. Okay, and we don't need to write because we've got 2 sodiums, we've got 2 nitrogens, and then we've got in total here we've got the right number of oxygens because we need to take that oxygen away from this because that's a product. And we put the value by the side, minus 359, and then we need to times it by 2 because it's forming 2 NaNO2s. This one here does not have a value, does not have, oh no, actually, when I say it does not have, it does have a value, but it's 0, and that's why we ignore it. That has a value of 0 kilojoules per mole. And why does it have a value of 0 kilojoules per mole? Because the enthalpy change of formation of 1 mole of a compound from its elements. It's an element, so it's already an element, so you can't form an element from an element. It's already an element. It will have a value of 0, and therefore we can just ignore in the enthalpy cycle. Right, so now let's apply Hess's law to this question. So that is exactly the same as going down and up, going down and up. That is the same as going down and up, okay? So the enthalpy change for the reaction is we're going to go down, single black arrows in the wrong direction, so turn it around, not on the enthalpy cycle, turn it around here in the calculation, 468 instead of minus, 468 times 2, and this one is going in the right direction, so and minus 359 times 2, don't forget the times by 2, and when you do that calculation your answer should come out at 218 kilojoules per mole. So you need to practice, you can pause it and practice it and make sure you get the same answer. Right, next question to try. There's a couple more questions to try. Next one, question 3. Okay, calculate the standard enthalpy change of this reaction. Okay, so just the same, standard enthalpy change of this reaction, okay? Alright, but the difference here is the information that we've been given, the data we've been given. Can you see that there? That symbol there? That is a C, which means that we've been given combustion information. So this is different because we've been given combustion information here. So the combustion of carbon. So when we combust carbon, we make CO2 gas. Okay, we need oxygen to do that. Just write it next to the arrow. And the arrow, can you see the black arrow is going in a different direction? We're taking carbon and we're combusting it and forming carbon dioxide. So the combustion, the arrow goes down. The single black arrow goes down. And we just write the value by the side, minus 393.5. We're combusting 1 mole of carbon. We do the same with hydrogen. And when we combust hydrogen, then we make water. We make water. But then we need to balance it because we've got 2, so we're going to make 2 waters. Okay, and then we're going to need oxygen again. I'm going to need another oxygen. And we put the value by the side. So the value is minus 285.8. But we're combusting 2 hydrogens, so we need to times it by 2. So combusting 2 hydrogens. And then when we're combusting methane, we form carbon dioxide and water. And it's already written there, so you don't have to do anything, it's already written there. And we need, in order to do that, we need 2 oxygens, but that's good because we've got 2 oxygens here, 1, 2, so that's good, we've got 2 oxygens. And just write the value by the side. Minus 890.3 kilojoules per mole. Right, so that's your enthalpy cycle, which is different to when it's formation. Right, remember when it's formation, the arrows go up, okay? When it's combustion, the single arrows go down, okay? Combustion goes down, formation goes up. But Hess's law always goes, that is exactly the same as going down and up. That way is exactly the same as going down and up. Okay, so your calculation will be enthalpy change of reaction equals standard enthalpy change of reaction equals going down. So we're going down these single arrows, these two single black arrows, and they're in the right direction, so we just keep them exactly as they are, minus 393.5. And the other one is minus 285.8 times 2. Just keep it exactly as it is. And this one here, we're going up, it's going down and up. We need to turn this single black-headed arrow around, so it'll become plus 890.3 and not minus. And you do that calculation, and the value comes out as minus 74.8 kilojoules per mole. Right, so let's try one further example, and we'll do this one quicker. Calculate the standard enthalpy change of reaction. So the standard enthalpy change of reaction, okay. Information, we have got combustion values, combustion data. So I know straight away I'm going down, 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 like that, okay, down for combustion. I write the number by the side, making sure I get the right one next to the right arrow. So minus 1411, it's only one, that's good. This one, minus 286, and there's only one of them, so that's good as well. And then minus 1560. Apply Hess's law. That is exactly the same as going down and up, going down and up. So my calculation for this enthalpy change of reaction is going to be, I'm going to go down, it's in the right direction, so I'll just keep it, and going down, it's in the right direction, so just keep it. You go down the reactants and up the products. I need to turn this one round because the single black-headed arrow is going the wrong direction, and that gives a value, when you do that, of minus 137 kilojoules per mole. Okay, the last question, which is an exam question, I hope you can read it okay, because it's not very dark. Okay, and you need to pause the video and have a go at this yourself. This is from an OCR exam paper. It's an exam question. Okay, so pause the video and have a go at it yourself. You've got your equation that you're trying to find. I'm going to write that at the top. And you get faster at these, get quicker at them, okay? I look at what data I've got, and I have got formation data. So I know it's formation, so that all the arrows are going to be going up. Nitrogen has a value of 0, so it doesn't have an arrow. I write the number by the side, 51, but there's 2 of them, so I times by 2. N2O4 is 9. For water is minus 242. I'm just copying it, minus 242 times 4, because there's 4 of them. The enthalpy change for this reaction, I need that is the same as going down and up, home, college, shops. Going down and up is exactly the same, okay? So I'm going to go down these 2 single black-headed arrows, so I need to go, so I need to change the sign, because the single black-headed arrows are going in the wrong direction, so I need to change the sign. So I don't change it here, I change it down in my calculation. So go minus 51 times 2, and minus 9, and this is going in the right direction, so I just keep it as it is because it's going in the right direction. And then that gives you an answer of, the answer of the calculator should give you the answer minus, you can do this on your calculator yourself, minus 1079 kilojoules per mole.